When I was a kid, I wanted to go to space, to be the first person to visit a new solar system or galaxy, to be the first astronaut to explore a new world. One of the issues with this, I now realize as a physicist, is time. The distances are so massive that it would take many lifetimes to get to the places that I dreamt of with the spaceships we currently have. But what about if we could build something that went faster, a lot faster? What would happen, for example, if a spaceship was able to travel at, or close to, the speed of light? Would this allow me to get to where I dreamt of going? Well, for this, we need to think in terms of theoretical physics. In particular, we need to use Einstein's theory of special relativity. Only by doing this can we start to get some answers. And I warn you now, it gets very weird indeed. Let's go to infinity and beyond. This is Think 4. The first and most important concept when dealing with special relativity is this. Light cannot travel faster than 3 × 10⁸ meters per second. If you are traveling forwards on a train and shine a torch forward, classical physics tells us that the speed of light would be the speed of the train plus 3 × 10⁸ meters per second. However, every measurement ever taken tells us that light cannot travel faster than 3 × 10⁸. So what happens? The answer lies in the simplest equation of them all. Speed equals distance over time. Taking this equation and applying it to this situation tells us this. If nothing can travel faster than 3 × 10⁸, then that side of the equation can't change. So if we have a situation where that should occur, something weird happens. Either the distance or the time has to adjust instead. If an object is traveling close to the speed of light, what an outside observer would see is the length of objects shrinking, or the time it takes them to appear where we are expecting them, expanding. These phenomena are known as length contraction and time dilation, and we have a set of equations to explain them. These are called the Lorentz equations. What they tell us is this. The closer to the speed of light we travel, the more dilated time gets, and the more contracted length gets. Let's take a look at length contraction. L prime is the contracted length that an outside observer would see. L is the length of the object, v is the velocity of the object, and c is the speed of light. So if a spaceship is 50 meters long and traveling at 50% the speed of light, or 1.5 × 10⁸ meters per second, we could call that 0.5 c, and we often do. Our equation would be L prime equals 50 times the square root of 1 minus 1.5 × 10⁸ divided by 3 × 10⁸ squared. Note, that fraction simplifies to a half, and that is why it is useful to say 0.5 c, as that fraction would just be written as 0.5 over 1. When we plug in our numbers, we get an answer of 43.3 meters to 3 significant figures. These equations are not tremendously difficult, but they are mind-bendingly strange results. The things to remember are, light travels at 3 × 10⁸ meters per second in a vacuum, no matter who is looking at it, no matter how fast you think it should be going. And if an object travels near the speed of light, we just need to drop the values into the Lorentz equations to see what an outside observer would see. Speaking frankly, I think my chances of getting to a new solar system or galaxy are probably pretty slim. Traveling at the speed of light sounds pretty cool, but I am not sure I fancy the being contracted part. For now, I'll stick to my own planet, which actually isn't so bad. I'll just use theoretical physics to imagine the rest. This was Think 4. Thanks for watching.